Hey, you're here. I'm here. It must be time for another algebra lesson. So let's do it. So we are at 5.2. So again, 5.2, the fundamental theorem of algebra. You should be able to see it right there. So anyway, what we're going to be doing is I can find complex roots of polynomials and complex solutions to polynomial equations. So think about what we did last time in 5.1. We were finding roots to polynomial equations. So here in 5.2, those roots can now include complex solutions. So remember things that involve I, as well as irrational solutions. So let's get going. So to spark our learning, the change in estimated value market, I can't read. The change in market value of a particular house over time period can be modeled by a cubic function. So some questions we'd ask: what is that function? When should we sell? Or when should we buy? Things like that. So we get our information answered. So here is our graph. And years since 2004, right down here on the bottom. Difference in value in thousands. So if I were selling a house, wanting to make as much money, here or here would be a really good spot to buy. I'm sorry, to sell. If I wanted to buy a house, buying down here would make the most sense because it's the cheapest price. And so actually a lot of people kind of try to play this market and you can make a lot of money on it, or you can lose a lot of money. Same thing. So me, for my house, I bought my house down here. We got lucky. It was during the most recent housing crash, or the first one I should say. So we got lucky. We bought down here, and so hopefully we'll someday make money on our house. So things that we can talk about. What is a model of change in a house's value over the time period? What variables are involved in this situation? What units of measurements are used in each variable? So we had years down here, and we had change in price up here. So for example, at our two zeros at the origin 0, 0 and 7, 0, the house was not worth 0. The house was just the same price as when it started right here. So that would matter for, like, if you were a housing agent, real estate agent, you want to buy a house when it is, or you want to be able to track the price of change of that house. Because selling a house doesn't do you any good if it's down here. So this would be some information that would be very useful for a real estate agent. What strategy or tool would you use along with all the information you have? Depends on what the question is, things like that, so on and so forth. All right, let's get started. So the fundamental theorem of algebra, again, seems kind of important. So we are going to investigate complex zeros of a polynomial. So here we are talking about multiplicity. So if you look right there at that top line, a zero of a polynomial function can appear in the factorization of a polynomial more than once. So if you have 1, 0, it could be more than 1 or appear more than once. When that happens, we call that a multiplicity. And if it appeared twice, it would be a multiplicity of 2. So in our example right here, we've got f of x equals x squared plus 10x plus 25. So if we were to factor that, so we would have x plus 5, x plus 5. So, or x plus 5 squared. So when we do that, it is said that we have a multiplicity of 2. So when you have one of your zeros, or one of your roots, I should say, raised to a power, that's where you get your multiplicity. So that's what that's all talking about right there. So the definition, the multiplicity of a 0 for a polynomial function is the number of times that 0 is a factor in the factorization of a function. So in this case, it is 2, or you can always look at the exponent right there. Okay, so let's move along here. So examine the relationship among zeros, multiplicities, and degrees and graphs of polynomial functions. So right now we're just kind of getting used to all the different things that we're talking about here. So if we look at these three graphs, we've got equations down here. We can factor them either based on the graph or based on the factors. So I'm going to go through and factor them real quick. So this first one, we can pull an x out, and then we have, and I'm just going to do some chicken scratch over here, and we have x squared minus x minus 6. So what, 2 and 3. So then we're going to have x minus 3, and then x plus 2. So that makes sense. So we've got our, if we add a negative 2 right there, there's our 0. Let's change my color. There's my 0. There's my 0 from that one. And there's my 0 of positive 3 from that one. Okay, so we move on to this next one. I'll get rid of some of my dots. Again, we try to factor this one. I'm going to pull that x out. Then we're going to have, again, x squared minus 6x plus 9. So that's going to be a plus 3. Whoops. So that's going to be an x and x plus 3. No, it's not. It's going to be an x minus 3. So you can check me by looking at the graph, x minus 3. So you'll notice that if I had put x plus 3, that would mean that there's 0 right there. There's obviously not one there. So I was kind of able to check myself because I saw that 0. Okay, let's get rid of that. So here we have our multiplicity of 2. So x equals 3 is a 0, but it is a 0 with a multiplicity of 2. And so we see that right there. Oh, come on, pen. There we go. So this last one, we just pull an x out, and then we have x squared plus 1. So our middle one has a multiplicity of 2. This one, so we've got one real root at the origin, but then we've got another root. So if we say x squared plus 1 equals 0, we're going to have x squared equals negative 1. So we do have a root. It's just at x equals plus or minus, what is it, I? Because we square rooted both sides. So we still have a root there, but it's imaginary. So it's not going to appear on the graph because the graph is only going to have real roots. So I'm going to leave those on the screen as I scroll down because I believe they're going to ask us for the factored versions. So if you want to see it all printed out nice and pretty, we've got x, that one, got this guy, multiplicity of 2, we got this guy. Yay! For now, I'm going to leave those on the screen because I have a feeling I might need them. So identify the real and complex zeros of the function f of x. So that was our first one. I guess we should go through and label these. This is f of x. This is g of x. H of x. So identify the real and complex zeros of function f of x and their multiplicities. Select all true statements. There is, what, 1, 2, 3 roots. Real zeros at 0, 3, and -2, all multiplicity of 1. Are you going to actually check it for me? No, it's not, but whatever. Is there another one? Real 0 of 3. No complex zeros. That's what I was forgetting. I thought that was obvious, but I should have said it. So this is for g of x. This is our middle one right here. We've got a root at 0 and a root at 3. There are no complex zeros. Real 0 of 3 with a multiplicity of 2. So that's these two right here. And then a real 0 of at 0, multiplicity of 1. So that's our x part right here. And then the multiplicity of 2. Well done. You didn't give up, and your effort paid off. I love those little encouraging things. They're so cheesy. Anyway, identify the real and complex roots of the function h of x. Remember, that's our third one. So we've got an imaginary number. So we have a real 0 of 0 with a multiplicity of 1, and then a complex 0 of -I and I, each with a multiplicity of 1. So again, that's this part right here. So what do you notice about the multiplicities of the zeros in relation to the degrees of the function? Let's see what we got. So the sum of multiplicities is less than the degree of the function. No, didn't get that one. What are they going for? Is equal to? There we go. So they're trying to get us to have a connection there. I guess they're talking about if we add all the multiplicities up. So this middle one had x with a multiplicity of 1, and then x, and then 3 with a multiplicity of 2. If you add those up together, that's 3, which is equal to the degree of the function. Consider the cubic function. So I think I can get rid of these now. The 0 of f of x is 0. The multiplicity is going to be 3 because of what we just figured out. The graph only crosses the x-axis at x equals 0. So again, our multiplicity added up to the degrees. So how does the multiplicity of a real 0 relate to the graph of the function? Use your answers from parts B and C to help you form a conjecture. Wow, conjecture. From parts B and C, where are those at? B, so those are all those. C. So the multiplicity is, we're talking about x cubed, is odd. The graph crosses the x-axis at 0. If the multiplicity is even, the graph touches but does not cross the x-axis at 0. So that is, again, just giving us a connection about how some of these things work. So if the degree of function is odd, that's going to tell us a certain thing, or even, again, it's going to tell us something. So the figure shows a graph of a fourth degree polynomial. Use your findings about the relationship among multiplicities of zeros, the degree of the function, and the end behavior of the graph around the zeros to predict the number of real and complex zeros for the function. So we're looking at our graph, and what can we figure out? So number one, we know that it's a fourth degree function. So our multiplicities has to add up to 4. So how many real solutions do you see on the graph? Now remember, the real solution is when the graph touches the x-axis. You will notice that there is only 1. So then, of course, are there any other real solutions or even irrational? So if it would cross in the middle of something like that, and there's not. And so when we look at it, so it is an even function, okay? And we know that if it was a regular degree, a fourth degree polynomial, like an x to the fourth, then it would be translated somewhere like that. But we've got this little bump right here. So that means that it's not that x to the fourth. And so some of our roots, or the other 3 roots, are going to be complex. So they're going to have I involved in there somewhere. So there's our sample answer. Oh, wait. That's kind of basically what I more or less talked through. So let's try one out. Apply the fundamental theorem of algebra. So the patterns we observed in the building understandings reflected in the fundamental theorem of algebra. So here is the fundamental theorem of algebra. Quote unquote. So every polynomial function of degree n greater than 1 has at least one root at least one zero, where a zero may be a complex number. Corollary, every polynomial function of a degree n greater than 1 has exactly n zeros, including multiplicities. So that's saying that a degree of polynomial, this part right here, so this part right here, every degree of polynomial has at least one root. Now, if you've got a graph that looks like this, and you've got your parabola, notice that the parabola never crosses the x-axis, but you will still have a complex root. So a 0 may be a complex number. So then to add on to that, a corollary, every polynomial function of degree n greater than 1, so n equals 2, n equals 2, degree of 2, degree of 3, things like that, has exactly n zeros, including multiplicities. So let's use it. So because the zeros of the polynomial function give the roots, the theorem and its corollary also extend to finding all roots of a polynomial function. That's what we're going to do. We are going to find all roots of some of our functions here. So let's try it out. So this next one says solve the polynomial function, polynomial equation, all of that. You can use the rational roots theorem. Remember, that's what we did last lesson. So with the synthetic division. So we know that the leading coefficient is 1. Therefore, all real rational roots are going to be a factor of negative 14. And they are listed right here. So at this point is where you would set up your little table. You've got your coefficients, 1, 7, -2, -14, and you're going to synthetic division the heck out of this, right? So you're going to start with 1, 2, 3, 1, 2, 7, 14, -1, -2, -7, 14. So they have conveniently already did all that for us. So here's their chart. So they did every single factor. Let's see here. I'm going to write down this equation here at the top, just so that I have it to look at. So here they went through and they did all of our synthetic division. So based on this chart, what is the real zero of this function? So at this point, you should be looking down here, and you find this guy right here, and you find that the remainder is 0, so that is a root of the function. So that would be like x plus 7, and then our coefficients would then be x squared minus 7x plus 96. No, where did I get 96? I was looking at the wrong line. Again, x squared, it's got 0, so it's just x squared minus 2. So, let's see what else I got for us. So how do you know -7 is the only rational root of the polynomial equation? So we tested them all, and that's the only one that came back with a 0 remainder. I'm not going to worry about answering some of these things. The degree of the polynomial is 3. So how do we know that? Remember, the degree is the highest number of exponent that we have associated with our variable. So in this case, the greatest exponent is 3. So we can apply the fundamental theorem of algebra to determine that p of x has 3 zeros. So again, degree of 3. So degree of 3. And if we graph it, it will tell us that the graph will tell us that we have a real root right there, but we have 2 more roots that are not rational. So the real rational root theorem helps us find these things, but it doesn't necessarily help us find these things. So you'll notice, though, after we factor this, we could probably use that to figure this out, right? So if I wanted to factor this further, I could do, so we still have the x plus 7. What was that? That was x squared minus 2, right? Right? Yeah, that was minus 2. I think I accidentally erased it. So I can't necessarily factor that, I'm sorry. What we can do is we can solve it, though. So that's where I was going with this. So x squared minus 2 equals 0. So we have x squared equals 2. So then we would have x equals square root of 2, plus or minus. So that, using algebra, is right here and right here. So the negative version is this guy. The positive version is that guy. So we have found all of our roots, both algebraically and graphically. So this is a good cheat that you can use with your graphing calculator. It won't always tell you, and especially, if I'm grading your test, I'm going to be looking for this stuff to make sure that you're doing the algebra correctly. But it will tell you like, oh, there's 3 rational roots that I need to find. So my answer probably needs to have 3 things. So the third one for here is x equals -7. So describe where the zeros are located on the graph. Select all that are true. We have a rational 0 at x equals -7. Located on the on the x-axis between -2 and 1. Yep. And then located on the x-axis between 1 and 2. You can see that the p of x crosses the x-axis 3 times, so all 3 zeros are real. So they just did algebra here, just like we did, and they solved that x equals -√2 and √2. So the roots are all of those. Are the equation's roots real or complex? So they are real. And yeah, so let's see here. All roots are real. 2 are irrational. 1 is rational. And there you go. Okay, so now our next job is to write a polynomial function given its zeros. So we started with a function in standard form, found the zeros. Now we're going to be given the zeros, and we need to find the function. So a couple of things we got to know. So we have these irrational conjugates, and then we have complex conjugates. So since we're dealing with things like x squared, x fourths, whatever, whenever you have x squared equals, 4, our x is going to be equal to plus or minus 2, right? So we take the square root of both sides. So then on the flip side, when we're going backwards, if we are given, hey, you have a root of +2 and -2, then you can use that as a quote-unquote conjugate. So that's what they're talking about here. So every time, let's see here. So the -√2 and the square root of 2 form a pair called irrational conjugates. These irrational root pairs can be written generally. There's your general formula, blah, 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 blah. When a polynomial equation has complex roots, these roots come in pairs called complex conjugates. That can be written generally. There's your general equation, such as 3 plus 6i or 3 minus 6i. So that's just a word that we're going to be using a lot, so get ready for that. So the irrational root theorem, if a polynomial p of x has rational coefficients and a plus b square root of c is a root of the equation, where a and b are rational and c square root of c is irrational, then a minus b square root of c is also a root. Translation, if you have this as a root in one of your functions, you also have its conjugate as a root. So that is basically what that is saying. So if you find an irrational root that has a square root in it, the conjugate of that square root is also a root. So the same thing with complex conjugate root theorem. So if you have this as a root, so if a plus bi, where a and b are real numbers, is a complex root polynomial equation with real number coefficients, then a minus bi is also a root. So once again, if you have this as a root, its conjugate is also a root of your p of x function, of your polynomial function. So both of these are saying is if you have one, then you're going to have the other. You're going to have the conjugate of that. So let's try it out. So write the polynomial function in standard form that has a leading coefficient of 1 with the least degree for the given zeros 1, 4, and 2 square root of 3. Use the irrational root theorem, blah, blah, blah. So if we're looking at these guys right here, so we know, based on those zeros, that our function, our p of x, is going to be, first we got x minus 1, that's where that 1 comes from, x minus 4, so remember these are zeros, so when these get plugged into here, it should make their little spot equal to 0. So then we've got this guy, so we're going to have x minus 2 square root of 3, because this is positive, we plug that in there, we're going to get a root. However, because of the irrational root theorem, we also have, oh, I ran out of room, x plus 2 square root of 3. So that is the conjugate. So these two are conjugates. So that's our start. That's where we get this part from. So why do you write it in factored form? Because we know the 4 zeros. What will be the degree of this polynomial? So it's going to be a degree of 4 because we have 4 roots. And if you just look, if you just multiply all these together, quote unquote, real quick, you know that you're going to have at least one x cubed in there. I'm sorry, x to the power of 4. And so then we math, right? So we math. So step 1 is I would multiply those together, and we could multiply these together all in step 1 if we wanted to. So they did just this first part. They did this part right here first. Boop. So if you look right here in this line, let's zoom in. That seems like a great idea, Mr. Lin. Let's zoom in. So they started here. They grouped these together. And when you add them out, or when you multiply them out, this center factor is going to disappear. And then you're going to have 4 times 3, because 2 times square root of 3 times 2 times square root of 3. You're going to have x squared. So this is the reverse of a difference of squares. So just so you're tracking. If you don't recognize that, you can FOIL this out. That's fine. Things will just cancel out, and that's fine. That works. So then they simplified this. Easy enough. That's where we're here. So then they FOILed this into there. That's where we got this guy. Then they FOILed their last one, and then combined like terms. So our math is going to get pretty fun, but it is quote unquote basic arithmetic. I put that in air quotes because that's where I make all of my mistakes. But it is technically basic arithmetic, but whatever. We'll survive together. So the final polynomial function is x to the 4th minus 5x cubed minus 8x squared plus 60x minus 48. Right? Easy? You can do it. Well, let's find out. All right, so here's our next example. This one's going to use some i's. So it should look very familiar as the square roots, but instead of square roots, we're going to use i's. So write the polynomial function given its zeros. Blah, 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 blah. Our zeros are there. So we can actually just go ahead and write that. So note or remember, a single complex number is this whole thing. So an imaginary number is just your negative 3i. But a full complex number is this whole thing. So if you can kind of get that in your head, if you remember that in your head, that might make some of this make a little bit more sense as we go. So anyway, we've got our first 0 is 6, x minus 6. So then our second 0 is x minus 5 minus 3i. Right? So then on top of that, we have the conjugate of this. So now the difference here is that my brain says that, oh, we should just do x plus 5 minus 3i. But, I mean, really, I guess it would actually turn out to be the same. But they want us to do x minus 5 plus 3i, like that. So that's our conjugate. So technically speaking, you know, if I, well, no, I take that back. So this is how you do our conjugate for imaginary numbers. Okay? So then from there, we just, math, as I like to call it. So let's zoom in on what we're looking at here. So we start ourselves out. We've got our x minus 3i, and then we've got our x minus our 0, but then we also have our x minus our conjugate. So just make sure that you don't forget the conjugates. Irrational numbers, the square roots, it's the x minus your square root number, x plus your square root number. For i's, for complex numbers, this is the sign that changes. So it's a little bit different. Try not to get those two confused. I'm sure that I will, so catch me on it. So then they're grouping these guys together, and that's where they get this whole business. Okay, so then they did, x times x, x times that, and then this times, and then this complex number times x, and so on and so forth. So they just multiplied all of that out, and they showed exactly what they were doing. So here's your x times 5 plus 3i. Here's your 5 minus 3i times x. Here's your 5 minus 3i times 5 minus 5 plus 3i. And then your x minus 6 is still out there. So then we simplify. Now remember, anytime you have an I squared, it's going to turn into a negative 1. So they combined like terms, found their I squareds right here. So then when they turned all of their I squareds into negative 1s, those turned into just constants, and then these i's should cancel out. So if you're doing the conjugates right, the i's should cancel out. If you have an I in your final answer, check your math, check something, because you're wrong. And then from here, it's just our regular Algebra 2 type algebra stuff, in air quotes. Multiply it out, combine like terms, and here we go. Make sense? So I'm intentionally not doing it all on the screen because, so from this part down, you should be able to do easily yourself. Technically, from this part down, you should be able to do, or at least follow along. I always get concerned that I'm taking up too much of your time just doing simple arithmetic. And I really want you guys focusing on the concepts. You got plenty of time in your homework to do simple arithmetic, right? So let's see here. Why are there 3 binomial factors of p of x? Complex roots come in pairs. That's true. Yeah, complex root zeros come in pairs. That's all it is. What happens with all the terms with imaginary unit I? We mentioned that when they are combined, they are eliminated. They should cancel out. If they don't, then you need to check your math. You know what? I feel like we need a word problem, don't we? Yes, this is a totally legit real-world application that I'm sure happens all the time. Because everybody wants to know when roller coasters are at the same height. So here we go. Solve a real-world problem by graphing a polynomial model. So when polynomial functions do not have integer coefficients, you can use a graphing tool like your graphing calculator to figure out where the zeros of the polynomials are. So the functions below model the height of the first 60 seconds of each ride. So we've got 2 roller coasters. We've got what? We have the Fear roller coaster, and then we have Storm. So Fear is RF and Storm is RS for roller coaster Fear, roller coaster Storm. Super creative. At what times are these roller coasters at the same height? Because that's really all we need to know, right? So we've got our time equations right here. T is in seconds after they start, and the functions will poop out a number in meters, right? I don't know what. Yeah, in meters. So we need to know when they're the same height. But we have the mathematical abilities to find zeros of a function. So what we need to do is we need to combine these in such a way that we can essentially figure out the zeros. And once we solve for that, then the t, whatever that equals, is when they're at the same height. So what you could think about, and this is the way I thought about it, is if we have HRF, roller coaster fear, and that's a function of t, and this is going to be true, they're going to be at the same height when they are equal to each other, right? So we can't really deal with something like that right now, but we can subtract both sides by 1. And anyway, we would have HRF minus HRS equals 0. So if you look at these, we would then just subtract one of them, combine all of our like terms, and we would have an equation looking something like this, but just equal to 0. And that is then something that we could then graph on our calculator and find the zeros. So that's what we're going to do. So we got to find the difference of the 2 functions. Another way to think about it is if you imagine 2 roller coasters or 2 dots or whatever, and the difference between them, you would find that by subtracting that. So when this difference gets infinitely small and it equals 0, they're going to be at the same height. So 2 different ways to think about it. It's the same thing. So find the difference of the two functions, so that the 0 is representing the time, the roller coaster is the same height. Does it matter which functions you subtract from the other? It does not. So, again, we had our little equation. See if I can pull it up. Nah. And so you could subtract 1 from either one. It doesn't matter. And so let's see here. What is our h of d? Yeah, so h of d is their subtracted function. So here we have one of their functions, and I forgot which one. It doesn't matter. Minus the other function. And then when you combine all those like terms, that you would have to make sure that you distribute the negative sign. This is what you get. So I'm hoping you're following me. I'm breezing through this because I don't want to waste your guys' time with just doing math. But again, we took one of these, subtracted the other one, and we got that. So now we can shove this into a graphing calculator. So we do that, we're going to get something that looks like this. So from here, and again, we have to interpret this, right? So every time where this line crosses the x-axis, that is a 0 of our function. And that means that is when their heights are equal. So this one right here, that doesn't make sense. We can't have a negative time. Also, we know that like imaginary numbers, we're in the real world, don't care. They're not going to be useful in this situation. So we're only looking for real numbers. So we see one right there, one right there, and one right there. But I believe they are looking for the first. Okay, maybe they're looking for all of them. Whatever, that's fine. So it appears from the graph that the roller coasters are at the same height at about 17 and 51 seconds. Go away, dots. So 17, 51, and there's one at 81 or something. I don't know. 81. We'll call it that. So why should you not include the 0 that occurs close to t equals 80? Probably because that's when the roller coasters are done, I would assume. So I read something that said that the function only works for, oh yeah, look at that. So the function only works for the first 60 seconds. So that's going to cross that out. So make sure we're reading these carefully. The function only works for the first 60 seconds. Hey, so that's 5.2. So try the check on learning and see how it goes. If it doesn't work, then I think there's another video that you could watch, right? So check it out. I'll see you in class.